Integration by parts. So in this section, we're going to look at a new technique for integration that's called integration by parts. Before we get to the actual technique, I must mention that we need to know all of these basic antiderivative formulas. If you do not know these, you are going to have a very difficult time when it comes to the testing for this course. You must know these. You must be able to bring them from your memory immediately. Integration by parts is developed from the product rule for differentiation. So we've learned that fg, if we take a product and find the derivative of that product, that's f prime g plus fg prime. All right, so let me just kind of rearrange this a little bit. I'm going to write this as f times g prime subtract f prime times g is equal to f times g prime. And now what I will do is, in a sense, integrate both sides. All right, so I'll apply, the integral to both sides of this equation. All right, so now since I have a difference on the left-hand side, I'm allowed to break that apart. So I have the integral of f times g prime minus the integral of f prime g is equal to the integral of f g prime. Now, in that first term, the integral of f times g prime, those are, in a sense, undoing each other, right? The integration and the derivative are undoing each other, and so we just have f times g. So we have f times g minus the integral of f prime g is equal to the integral of f g prime. Now, what we usually do is we think of that, we switch the sides of this equation. So switching the sides, fg prime, the integral of fg prime is equal to fg minus the integral of f prime g. And most textbooks, most sources use a different notation. And basically the notation says represent the f, right? Let that be represented by u, and let the g be represented by v, and instead of using primes, we use the differentials, the d's. So then fg prime, we generally write this as the integral of u dv is equal to uv minus the integral of v du. And this is the formula for integration by parts, and is the second major technique for integration. I mean, really, there's only two techniques for integration: substitution and parts. And so now we're learning the second major technique. So for example, suppose we were asked to evaluate the integral of y times e to the 0.2y dy. If we tried a substitution, right? If we tried a sub, right? If we try a u sub and we let u equal 0.2y, then du would be 0.2 dy. And so notice that y causes an issue. We cannot just get rid of that y. So a simple u substitution doesn't work. So here's what I'm going to do. I'm going to try this new technique. I'm going to try this by parts. All right, and so here's how it works. We make substitutions. We make two substitutions. I'm going to let u equal y. And I'm going to let dv be everything else that's in that integral. So that would be e to the 0.2y dy. Now I'm going to find the differential. So then du equals dy. And I'm going to find the antiderivative. And so through a substitution, v would equal 1 over 0.2 e to the 0.2y. If you need to review that idea, that would be back in a previous section on exponential functions. All right, so now I've got my u and my v, and I've made the substitutions for u and dv, and I found respectively the du and the v. So the integral, right, this is the integral of u, and everything else here was the dv. The integral of u dv, this, which I'll call I, this integral is equal to u v y times 1 over 0.2 e to the 0.2 y minus the integral of v 1 over 0.2 e to the 0.2 y du, which in this case is dy. So understand, this was the u v minus the integral of v du. Now we can simplify things. So let's see. 1 over 0.2, 0.2 is 1/5, so 1 over 1/5 is 5. So the first term becomes 5y e to the 0.2y minus, and now we have this other integral. Well, I can bring that 1 over 0.2 outside again. Again, that's a 5. And so I now have 5 times the integral of e to the 0.2y dy. And that's a relatively simple integral. So I'd have 5y e to the 0.2y minus 5 times, and again, this would be a 1 over 0.2 e to the 0.2y, and we'll add the constant here. And so we get 5y e to the 0.2y minus 25 e to the 0.2y plus a constant. And so there's the integral, there's the indefinite integral using the integration by parts technique. We can always check our work with differentiation. And now this actually might be a good idea, a good time to try this. So let's now check with differentiation to show that this was a correct antiderivative. All right, so let's take d by dy of 5y e to the 0.2y minus 25 e to the 0.2y plus a constant. All right, so let's see, I would have 5 times, I have to use a product rule here, I would have y times e to the 0.2y times 0.2 plus the derivative of y with respect to y is 1, and I'd have an e to the 0.2y minus 25, and then the derivative of e to the 0.2y is e to the 0.2y times 0.2. And then the derivative of the constant is a 0. So let's see, I have 5 times y times 0.2, 5 times 0.2, that's 5 times 1/5, that's 1. So I've got a y e to the 0.2y. 5 times 1 times e to the 0.2y, so that's a plus 5 e to the 0.2y, minus 25 times 0.2, that's 25 times 1/5, that's 5 e to the 0.2y, and again plus 0. And notice that those terms, those e to the 0.2y terms go to 0, and we are left with y e to the 0.2y, which was the original integrand. So you might say, well, why did you make those choices for the u and the dv? Well, the truth of the matter is I have some experience with it. But in general, one approach is to think that we want to end up with a simpler integral. And so we usually choose the u to be the function that becomes simpler when differentiated. And then whatever remains is the dv. Now, some textbooks and internet resources recommend this LIATE, this acronym or mnemonic device, to help us give something that works most of the time. It doesn't work all the time, but most of the time. And what it says is, here's what you should choose for the U. All right, so choose for U, and in this order. So your first choice is a logarithmic function. Then the next choice would be an inverse trig function. So inverse trig. The A stands for algebraic. All right, so this includes, polynomials. This includes radicals, rationals. The T stands for standard trig functions, and the E stands for exponentials. This works most of the time. Not always, though. All right, so let's look at another example. Here we're asked to evaluate the integral of p squared natural log p with respect to p. All right, so using the LIATE acronym, I would let the u be equal to the natural log of p, and the dv to be everything else. So that's p squared dp. Differentiating the u, du is equal to 1 over p. Integrating the dv, finding the antiderivative, v would be, 1/3 p cubed. And I do need here that du is 1 over p dp. I can't forget that differential. All right, so then my integral would be equal to uv, natural log p times 1/3 p cubed, minus the integral of v, 1/3 p cubed, du, which is 1 over p dp. All right, so there's my side work. And now I'm rewriting the integral using parts. So we have 1/3 p cubed natural log p minus, I can bring that 1/3 out, that's a constant, and I have remaining under the integral p cubed times 1 over p, that's a p squared dp. And now this is easy. 1/3 p cubed natural log p minus 1/3 of 1/3 p cubed. And we'll add in our constant from integration. And so we get 1/3 p cubed natural log p minus 1/9 p cubed plus a constant. And so the integral is given. What if we were asked to evaluate the integral just natural log x dx? Well, there's really only one thing to choose for the u. I'm going to choose for u natural log x. And then whatever's left becomes the dv. So dv is simply dx. All right, so then, let's see, du would be 1 over x dx, and then v would simply be x. Right, the antiderivative of 1 dx is x. All right, so then my integral would be given as uv natural log x times x minus the integral of v du x times 1 over x dx. And so then the integral, usually we would write that as x natural log x minus the integral, let's see, we have the x times 1 over x is simply 1 dx, and that's an easy integral, x natural log x minus x plus a constant. All right, so the antiderivative of natural log x is x natural log x minus x plus the constant from integration. How about the antiderivative of sine inverse x dx? Again, this would be a good time for you to pause. Try this one out on your own. Using a similar technique as in the previous exercise, I'm going to let u equal sine inverse x and dv equal du. Or I should say dv equals dx, sorry. If u is equal to sine inverse x, so then the du is 1 over the square root of 1 minus x squared dx. And if dv is dx, then v is x. So then the integral is given as uv, so sine inverse x times x minus the integral of v du, x times 1 over the square root of 1 minus x squared dx. And so then the integral is, and again, normally we would write that as x sine inverse x. And I'll write that integral as, well, let's see. I've got that x, and I've got that square root of 1 minus x squared. What if I made a substitution here? Well, let me write it first as x over the square root of 1 minus x squared dx. I'll write it like that. Now I'm going to make a substitution. See, I've got to figure out this integral still. What if I let, I'm going to use a new variable here. I don't want to use u or v because they've already been used. What if I let, say, t equal 1 minus x squared? Then dt would be negative 2x dx. And I've got the x and I've got the dx, so I would need a negative 2 and I would need a negative 1/2. So then my integral is x sine inverse x plus 1/2 of the integral of 1 over the square root of u du. I shouldn't have u, I should have t's there. Sorry about that. 1 over the square root of t dt. And so that's the integral of t to the negative 1/2 dt, which is t to the positive 1/2 over 1/2, which is 2t to the 1/2. So my integral is x sine inverse x plus 1/2 times 2t to the 1/2 and plus a constant from integration. Substituting back in terms of x, integral is x sine inverse x, 1/2 times 2 is 1, so plus, and t to the 1/2, I'm going to write that as the square root of 1 minus x squared, substituting back, and plus the constant. Here's another one that I would suggest that you try. This one's a little tougher. You're going to have to use integration by parts twice on this one. All right, using the LIATE thing, I see an algebraic and a trigonometric. So I'm going to choose the u equals t squared and the dv equals sine beta t dt. So if u is equal to t squared, then du is equal to 2t dt. And if dv is sine beta t dt, using a mental substitution, letting u of beta t, then v is 1 over beta let's see, it would have to be negative 1 over beta cosine beta t. Right, because the antiderivative of sine is negative cosine. Alright, so now using parts, the integral would be uv. So let's see, simplifying that, that would be negative 1 over beta t squared cosine beta t minus the integral of v du. So let's see, that would be a 1 over beta cosine, I missed the negative there, negative 1 over beta cosine beta t times 2t dt. Alright, so I've got negative 1 over beta t squared cosine beta t plus, let's see, I can factor out the 2 and the over beta. So plus 2 over beta integral t cosine beta t dt. Alright, so now we have to deal with this integral. Alright, so on this integral, a simple substitution won't work because of that t. So again, I see this combination of an algebraic and a trigonometric, and so I'm going to now make the substitutions. I'm going to use m and n now, just so there's no confusions. I'm going to let m equal t and n equal cosine beta t dt. If m is equal to t, then dm is dt, and n would be, let's see, we'd have to have 1 over beta sine beta t. Alright, so then my original integral is equal to, let's see, I have negative 1 over beta t squared cosine beta t plus 2 over beta times, now here's the parts again, uv, so that's mn, so that would be t times 1 over beta sine beta t minus the integral of v du, which in this case is n dm. So 1 over beta sine beta t dt. Alright, so let's see, this negative 1 over beta t squared cosine beta t, distributive property. I've got a 2 over beta times t times 1 over beta. So that's a plus 2 over beta squared t sine beta t. Plus, and then I've got a minus, and I've got a 2 over beta, and I've got another 1 over beta, so minus 2 over beta squared integral sine beta t dt. Now this antiderivative of sine beta t dt would be negative 1 over beta cosine beta t plus a constant, and actually we saw that earlier in our original substitutions. So after we clean this all up, our integral is negative 1 over beta t squared cosine beta t plus 2 over beta squared t sine beta t. Then I've got a negative 2 over beta squared times a negative 1 over b, so that would be a plus 2 over beta cubed cosine beta t and a constant. Alright, another example. Here we have a definite integral of x squared plus 1 e to the negative x. And for the moment, for a little while, I'm not going to worry about that 0 to 1. We're going to work with everything else. I'm going to find the antiderivative, and then I'll go ahead and substitute. Alright, so letting u equal x squared plus 1, and dv equal e to the negative x dx. Then du would be 2x dx, and v would be negative e to the negative x. So then my integral would be uv, so that's x squared plus 1 negative e to the negative x times negative e to the negative x minus the integral of v du. So I'd have a negative e to the negative x by 2x dx. So I would have x squared plus 1 times negative e to the negative x. And notice I have this negative and this negative, so plus 2 times the integral of x e to the negative x dx. Making another substitution. I'll let m equal x and dn equal e to the negative x dx. Then dm is dx, and n is again negative e to the negative x. And so my integral becomes x squared plus 1 times negative e to the negative x plus 2 times, now that integral becomes uv, so that's mn, so that's x by negative e to the negative x minus the integral of n dm, negative e to the negative x dx. Alright, so my integral, x squared plus 1 by negative e to the negative x minus 2x e to the negative x minus minus, so plus integral of e to the negative x dx. Alright, I guess I could have brought that negative, I can bring this negative out if I want, so just to make it a little bit cleaner. So I've got a negative x squared plus 1 e to the negative x minus 2x e to the negative x, and then the antiderivative of e to the negative x is again a minus e to the negative x. Now I'm not going to worry about the plus c in this case because I've got a definite integral. So now I'm going to evaluate that indefinite integral on, or from 0 to 1. Alright, so that would be I of 1 minus I of 0. Alright, so I of 1, let's see, if x equals 1, I'd have 1 squared plus 1, so negative 2e to the negative x minus 2 times 1 minus 2e to the negative, I should say negative first, this negative 2e to the negative 1 minus 2e to the negative 1 minus e to the negative 1. Subtract now I of 0, 0 squared plus 1. Now e to the 0 is 1, so I'd have a negative. 0 squared is 0 plus 1 is 1, so negative 1 e to the 0 is 1 minus 2 times 0. Okay, so minus 0 minus e to the 0 is 1. And I realized that I forgot to distribute that 2 here. So that should be a 2 here, and this should be a 2 here. Sorry about that. And so then after all this simplification, let's see, I've got negative 2e to the negative first, minus 2e to the first, minus 2e to the negative first, so that's a negative 6e to the negative first, and let's see, minus a negative 3 plus 3. Negative 6e to the negative first plus 3. Not a lot of fun, but we got it done. Alright, and for our last exercise, we have the integral of sine inverse x squared dx. Alright, so this one's It's a little tougher. You might want to go ahead and pause and try this one on your own before I do it. All right, so I will let u equal that entire sine inverse x square, leaving for dv the dx. Then the du would be 2 sine inverse x times the derivative of sine inverse x, which would be 1 over the square root of 1 minus x squared, and we'll throw in the dx as well. And so then v would equal x. All right, so there's my side work. Now by parts, I would have sine inverse x squared times x minus the integral of, let's see, we would have uv minus v du, so x times 2 sine inverse x times 1 over the square root of 1 minus x squared dx. All right, so this gives us then x sine inverse x squared, and now minus 2 times, let's see, I'd have an x sine inverse x over the square root of 1 minus x squared dx. Now, here's where life gets a little tricky. It seems like a substitution might work here. So I'm going to let t on this integral. What if I let t equal sine inverse x? Well, then dt would equal 1 over the square root of 1 minus x squared dx. And I almost have that. I've almost got it. I've got the 1 over the square root of 1 minus x squared, but I've got this x to deal with. So here's what I'm going to say. If t is sine inverse x, then x is sine t. So then that integral of x sine inverse x over the square root of 1 minus x squared dx can be written as the integral of sine t times sine inverse x is a t, and the 1 over square root of 1 minus x squared is the dt. And now this, I'm going to integrate by parts again. And I'll integrate by parts with m equal to t and dn equal to sine t dt. So then dm would be dt, and n would be negative cosine t. And so that would then be, let's see, mn, so that would be negative t cosine t minus the integral of n dm, negative cosine t dt. And so that's negative t cosine t plus the integral of cosine t, so that would be a plus sine t plus a constant. All right, so now back in black, my original integral would be x times sine inverse x squared minus 2 times, and now that whole integral ends up being negative t cosine t plus sine t, and then we have that constant. We can bring the constant outside. But we've got to get this back in terms of x. So the integral is x sine inverse x squared plus 2. Now t was sine inverse x. But wait a second, what would the cosine of t be? Well, if t is sine inverse x, then we can draw a reference triangle with sine, for the sine to be x, we would have opposite over hypotenuse, x over 1. Solving the triangle using the Pythagorean theorem leaves square root of 1 minus x squared for the remaining side. Then the cosine of t would be the square root of 1 minus x squared over 1. And then the sine of t, well, that would be, so negative 2 times sine t, that would be a minus 2, and times the x, because sine t is x, and then plus a constant. So that one was not pretty. We had to use a couple of different substitutions and some inverse, some work with our inverse trigonometric functions. All right, that concludes the presentation on integration by parts.